Hey, Math 1050, this is section 8.3, talking today about geometric sequences and series. There are 5 topics. So the first topic is to identify a geometric sequence and find the common ratio of a geometric sequence. So a sequence is geometric if the ratio of consecutive terms is always the same. So we're talking about a common ratio this time. So just to compare to last time, our last section was arithmetic sequences. So maybe if I had an arithmetic one, I would have a common difference of maybe 4, and that means my sequence would be 5, and then 9, and then 13, and so forth, adding 4 each time. Well, this time we're talking about geometric sequences, so it's a common ratio. We're multiplying by the same number. So if I had a geometric sequence that started with 1 and had a common ratio of 4, the first term might be 1, the second term would be 4, then it would be 16, and then 64. Where I multiply by 4 each time to get the next term. So adding is arithmetic, and multiplying to get each term would be geometric. So this topic, we're looking for geometric sequences. So you just want to check the terms and see if there's something that you can multiply by over and over again to get that sequence of terms. So if I want to get a 2, 4 times 1/2 is 2. And I just want to check and see if that same ratio works again. 2 times 1/2 is 1. 1 times 1/2 is 1/2. So this is a geometric sequence, and that common ratio is 1/2. So the number that you multiply can be a fraction. The next sequence here goes from 2 to -10. Well, if I'm thinking about multiplication, that's timesing by -5. And it looks like that works each time if I multiply by -5, I get that next term. Now, if you look at two numbers and you're like, oh, I can't tell what to multiply by, just take each term, like maybe I take that 250 and divide it by the previous term. And that should work with every term and its previous term. And you should, if it's geometric, you'll get that same ratio each time. So this one is also geometric, and the ratio is -5. Okay, the last one over here on the side, I have a 6, and then an 8, and then a 10, and then a 12. So it looks like what's happening is that we're adding 2 each time. So that would be not geometric. That would be an arithmetic one like we talked about last time. Okay, so our next topic is kind of the same thing, but this time we will have to select whether the sequence is arithmetic, geometric, or neither. So just look at the terms and see, is there something I can times by or something that I can add to get each sequential term. So it looks like on this time, this is timesing by 4. 5 times 4 is 20. 20 times 4 is 80. So that's geometric. And it's not asking, but I'll just write down that the common ratio is 4. The next one down goes from 4 to 9 to 15. It's not timesing, but it doesn't look like adding works either. Because it's not the same each time. We have this 6 that's different. So that would be neither arithmetic or geometric. And then at the bottom, let's see, it goes from 18 to 13, from 13 to 8, from 8 to 3. It looks like we're subtracting 5 each time. So that would be arithmetic with a common difference of -5. All right, so for the next topic, our goal is to write an explicit rule, or basically an equation. So our equations are going to look like A of n equals, some thing with an n in it. So some of our sequences are going to be arithmetic, some of them are going to be geometric. So I have this excerpt from your formula sheet. For an arithmetic sequence, we'll use this formula to write our rule or our equation. For a geometric sequence, we will use this rule to write our equation. So for geometric, since we're just multiplying by that common ratio over and over again, it's like a little exponential. With r to the power n minus 1. We'll talk about the other stuff on that formula sheet in a minute. So our first sequence here goes from 15 to 20 to 25. So it looks like we're adding 5 each time. So that makes it arithmetic. So we're going to use this formula to write our equation. So it looks like A1 is 15, that's the first term, and our difference is 5. So our equation is going to be 15 plus n minus 1 times the common difference of 5. So Alex is going to want you to clean this equation up. So we need to distribute the 5. So this is 15 plus 5n minus 5. And then we can combine the like terms here, the constants. So this is 10 plus 5n. And that would be our equation. Or you could write it as 5n plus 10 if you wanted. Either way would be fine. For this one, our first term is 7, and then it's 14, and then it's 28. So it looks like we're multiplying by 2 times 2 times 2. So that means our first term is 7. Our common ratio is 2, and that's what we need to use to write our equation for a geometric sequence. Our equation is a to the n equals the first term multiplied by the common ratio to the n minus 1 power. I like to write it this way. It's also possible to see it like with a multiplication dot like that, but I think this way will probably be faster to type into Alex. You don't want to, you need something so that it doesn't look like a 72. So either put the 2 in parentheses or use a multiplication dot. Oh, and I didn't mark, that was geometric because it had that common ratio. Okay. All right, the next topic is to find the sum of the first n terms of a geometric sequence. So these are called series usually. So we can find the sum by adding up each of our successive terms. Of course, it would be possible if you had all those terms to manually type it into your calculator, but especially if you have a lot of terms, that becomes impractical. So we have a formula that we can use to get our answer more quickly. So for a geometric sequence, the sum of the first n terms is the first term multiplied by 1 minus r to the n power over 1 minus r. So to calculate the sum, we just need to know 3 things. We need to know the first term, we need to know the common ratio, and we need to know how many terms there are. So for our first sequence, our first term is 4. You can see it right there. The common ratio, well, the first term is 4, the next term is 16. Like they're adding a power of 4. It's being multiplied by 4 each time. So our common ratio is 4. And then we need to know how many terms there are. Well, this is the first term, this is the second term, this is the third term, and so this would be the 8th term. So it looks like n is equal to 8. So if I use my formula, the sum of the first 8 terms is going to be the first term multiplied by 1 minus the common ratio to the power n over 1 minus the common ratio. And if we calculate that in our calculator, we get 87,380. Okay, so our next sequence here that we're going to add up into a series is 5 plus 5 times negative 1/4 plus 5 times negative 1/4 squared, all the way up to 5 times negative 1/4 to the 4th. Please note on these fractional ones, Alex does not want a decimal answer. So make sure you leave your answer in fraction form. Okay, so our first term in this series is 5. Our common ratio is negative 1/4. So we're multiplying by another factor of negative 1/4 for each successive term. And thinking about the number of terms here, this is our first term, our second term, our third term. So this would actually end up being the 5th term. You can see that the term number is 1 higher than the power, and that's because this one, it's kind of, I guess, like a 0 power. So we have 5 terms in total here. So the sum of those 5 terms is going to be the first term multiplied by 1 minus the ratio to the n power over 1 minus the common ratio. And if we calculate that, we get 1,025 over 256. Now, I would like to note that some of these your calculator will be able to handle, and will put it into fraction form nicely, like this one did. But if it doesn't, calculate the numerator and the denominator separately, and you may have to do some simplifying yourself by hand to get that answer. So if you need some help with that, let me know. But we do need our answer to be in fraction form. Okay, so a couple more. These ones are using what's called summation notation. And at first, these kind of look a little bit tricky. The notation is a little bit weird. Might be the first time you're seeing it, but honestly, these ones are easier as soon as you understand what this notation means. So this symbol is a Greek letter sigma. It means that we're going to add a bunch of stuff up, and it tells you, that number on the bottom tells you which value to start your substitution with. So we're going to start by subbing in 1. So our first term would be 3 times negative 1/2 to the 1 power, which is negative 3/2. And then our next term, we would sub in 2. And that would give us 3/4. And then we would sub in 3. That's negative 3/8, and so forth. And then the number at the top tells you where to stop. So the last one that you would sub in is 9. So our last term would be 3 times negative 1/2 to the 9th power. So you don't need to write out what I wrote out. I just wanted to show you, what it is and what that means. But in order to figure out the sum, we don't need to have a list of terms. We just need to know 3 things. We need to know the first term. Well, we got the first term by subbing in that first j value, j equals 1. So our first term is negative 3/2. We need to know the common ratio. Well, the common ratio is just the base of that power. It's negative 1/2. And then we also need to know how many terms, but the sigma notation is telling you how many terms at the top. it's telling you to stop when you get to 9. So we start with 1 and we go up to 9, and that's 9 terms. So the sum of those first 9 terms is going to be the first term multiplied by 1 minus the common ratio to the n power over 1 minus the common ratio. And if we calculate that, we get negative 513 over 512, which is a lot easier than figuring out all those terms and adding them up. Okay, so let's try that one more time since that notation is new. So we need to know the first term. That's 4 times 3 to the power 1, so that's 12. We need to know the common ratio. Well, the common ratio is just the base of the exponent, which is not 1. I don't know why my pen wrote 1. I literally was writing a 3. Okay, and then we also just need to know how many terms we're adding up. Well, we start at 1 and go up to 7, so we have 7 terms. So we can calculate our sum. The sum of the first 7 terms, or the sum of 7 terms of this sequence, are the first term multiplied by 1 minus the common ratio to the power n over 1 minus the common ratio. And if we calculate that, we get 13,116. Okay, so on those last few examples, we were adding up a fixed number of terms. We added up 4 terms, or we added up 5 terms, or 9 terms, or 7 terms. Well, it's possible sometimes that we would like to add up an infinite number of terms. So if we have a geometric sequence, and as long as the common ratio's absolute value is less than 1, then we can find the sum of all of the terms, an infinite number of terms, and it's that the sum is equal to the first term divided by 1 minus r. So I want to talk about this for a second. Absolute value of r less than 1, that means that our r value has to be between -1 and +1. It also cannot be 0, because that would just be a bunch of zeros. All right, so if that common ratio for your geometric sequence is greater than 1, then the infinite sum does not exist. You can always find a partial sum, but the infinite sum does not exist. Okay, so we want to compute this sum below. I want to point out how you know it's infinite. On this one, we know it's infinite because of the ... means it's going on forever. And on this one, we know it's infinite because of that infinity symbol on top of the summation. It means added up, infinite number of terms. Okay, so our first term here is 2 times -3 to the -3/5. So that's -6/5. That's our first term. And the common ratio here is -3/5. And that common ratio is okay. The absolute value of -3/5 is less than 1. So we can use this formula. So the sum is just the first term divided by 1 minus the common ratio. And if we calculate that, we get -3/4. So we don't want any decimal approximations here. We want that exact value. So it's -3/4. All right, so the next one, our first term is going to be 4 times 1/2 to the power 1. So that's 2. And our common ratio, the base of that exponent, is 1/2. That is less than 1, so we are good to use our formula. So the sum is the first term over 1 minus r, and if we calculate that, we get a sum of 4. Okay, So you need to be very careful to not make an error with this formula. So we've got another infinite sum here. The first term of this would be 2 times negative 2 to the power 1. That's negative 4. The common ratio here is negative 2. So we cannot use our sum formula. And that's just because the common ratio is not less than 1. So the sum does not exist. And then on this one, again, it's infinite because of the dot, dot, dot right there tells us that we have infinite number of terms. So our first term is negative 4. Our common ratio is also negative 4. The absolute value of negative 4 is not less than 1, so there is no sum here. So just be really careful that you only apply the formula in cases where you can apply the formula, because you can absolutely fill in these numbers, negative 4 over 1 minus negative 4, but that's not actually going to give you a correct sum. This formula only works if the common ratio is between negative 1 and 1. Okay, I believe that is it for this section, so thanks a lot. Let me know if you have any questions.